Here is a statement that comes directly out of modern physics. The maximum amount of information that can exist inside a region of space may be determined not by its volume, but by its surface area. That is not philosophy. It is a conclusion forced on us by black hole thermodynamics. When matter falls into a black hole, the black hole's surface area increases in precise, measurable steps. And the entropy, the information content, of that black hole turns out to be proportional to the area of its event horizon, not the volume inside it. That single result changes everything. Because if the information describing a three-dimensional region is encoded on a two-dimensional boundary, then the inside may not be fundamental at all. What we experience as depth, distance, and volume could be a projection of data stored on a lower dimensional surface. This is not a science fiction claim. It is known as the Holographic Principle, and it emerged not from speculation, but from trying to prevent physics from contradicting itself. If this principle is correct, then space itself may not be fundamental. Gravity may not be fundamental. Even the fabric of reality may be an emergent effect of underlying information. Tonight, we are not asking whether the universe is an illusion. We are asking something far more precise and far more unsettling. Is the three-dimensional universe we experience a projection of information encoded on a distant cosmic boundary? The holographic principle did not begin as a bold theory about reality. It began as a problem. In the 1970s, physicists studying black holes discovered something unexpected. According to classical general relativity, anything that falls into a black hole is lost behind the event horizon forever. From the outside, all you can measure is the black hole's mass, charge, and angular momentum. Every other detail disappears, but quantum mechanics does not allow information to simply vanish. In quantum theory, information about a physical system is never destroyed. It can be scrambled. It can be dispersed. It can become practically unrecoverable. But it cannot be erased from the universe entirely. This created a direct conflict between gravity and quantum mechanics. If a black hole evaporates, as predicted by Hawking radiation, and disappears completely, what happens to the information that fell into it? If the information is gone, quantum mechanics is wrong. If it survives, then it must be encoded somewhere. The key breakthrough came from calculating black hole entropy. When Jacob Bekenstein and later Stephen Hawking worked through the thermodynamics, they found something deeply counterintuitive. The entropy of a black hole is proportional to the area of its event horizon, not the volume inside it. That is not a small detail. In ordinary systems, entropy scales with volume. Double the volume and you roughly double the information capacity, but a black hole does not behave like an ordinary system. Its information content scales with surface area. That single result suggested a radical possibility. Perhaps the maximum information that can exist inside any region of space is limited by its boundary, not its interior, its boundary. And if that is true for black holes, the next question becomes unavoidable. Why would it not be true for the universe itself? To understand how radical this is, we need to be precise. In everyday physics, the information content of a system scales with its volume. If you double the size of a gas container, you roughly double the number of particles it can hold, and therefore the number of possible microscopic configurations. More volume means more degrees of freedom. That intuition works everywhere. until you include gravity. When gravity becomes strong, something different happens. If you try to pack more and more energy into a region of space, at some point it collapses into a black hole. And once that happens, the maximum entropy of that region is no longer proportional to its volume. It is capped by the surface area of the event horizon that forms. This leads to a hard limit, known as the Bekenstein bound. There is a maximum amount of information that can exist within a given region of space, and that maximum grows with the area of the boundary, not the volume enclosed. That is not a detail about black holes alone. It is a statement about gravity and information together. If you attempt to store more information inside a region than the boundary allows, the system collapses. The geometry of space reorganizes itself to enforce the limit. In other words, space-time itself responds to information density. This flips the usual hierarchy. We tend to think of space as primary, and matter or information as something that lives inside it. But these results suggest something closer to the opposite. The amount of information may determine the structure of space. At this point, the logic tightens. If the information describing a three-dimensional region can be fully encoded on a two-dimensional boundary, and if gravity enforces that limit, then the interior description may not be fundamental. It may be redundant, which leads to the central question of the holographic principle. Is the three-dimensional world we experience simply a different way of describing information that fundamentally lives on a lower dimensional surface? At this stage, the idea could have remained a strange property of black holes. But in the 1990s, something happened that forced physicists to take it seriously as a universal principle. Juan Maldacena proposed a precise mathematical correspondence between two very different kinds of physical theories. On one side, a theory of gravity defined in a higher dimensional space. On the other, a quantum field theory without gravity defined on the lower dimensional boundary of that space. The claim was not philosophical, it was exact. Every physical process occurring in the higher dimensional gravitational universe could be mapped, one-to-one, onto processes occurring on its lower dimensional boundary. Nothing was lost. No approximation was required. The two descriptions were mathematically equivalent. This is now known as the ADS/CFT correspondence. In this framework, gravity in the bulk space emerges from quantum interactions on the boundary. The bulk is not an independent layer of reality. It is a different description of the same underlying information. If that sounds abstract, focus on the core point. A universe with gravity can be fully described by a theory without gravity, defined in one fewer spatial dimension. That is not metaphor. It is a working tool in theoretical physics. Thousands of calculations over the past decades have confirmed the internal consistency of this duality. Now, our universe is not exactly the same as the anti-de Sitter space used in Maldacena's original model. The geometry is different. The cosmological constant has the opposite sign. So the correspondence is not yet a complete description of our cosmos, but the structural lesson remains. Gravity, space-time geometry, and even distance itself may not be fundamental ingredients. They may emerge from a deeper, non-gravitational description encoded on a boundary. The holographic principle stops being a curiosity about black holes and becomes a candidate blueprint for reality itself. If a higher dimensional gravitational world can be equivalent to a lower dimensional quantum system, then what we experience as depth, curvature, and motion through space may be secondary, a large-scale reconstruction of more basic information theoretic relations. The question is no longer whether black holes store information on their surface. The question is whether the universe as a whole is doing the same thing. If the holographic principle is more than a mathematical curiosity, then we have to accept a difficult possibility. Space itself may not be fundamental. In general relativity, space-time is the stage on which physics happens. Matter moves through it. Energy curves it. Gravity is geometry. But in holographic duality, geometry is not primary. It is derived. In the boundary theory, the lower dimensional quantum system, there is no gravity and no extra spatial depth. There are only quantum fields interacting according to well-defined rules, yet when those interactions are translated into the higher dimensional description, they produce a curved space-time with gravity. The bulk geometry emerges from quantum relationships on the boundary. This leads to a very specific idea: space-time may be built from patterns of quantum entanglement. Entanglement is not a vague concept. It is a measurable correlation between quantum systems that cannot be explained classically. When two particles are entangled, the state of one cannot be fully described independently of the other. Over the past decade, research has shown something striking. The strength and structure of entanglement in the boundary theory directly determine the geometry of the bulk spacetime. Change the entanglement pattern, and the shape of space changes with it. Reduce entanglement far enough, and spacetime can effectively tear apart. In this view, distance is not a primitive feature of reality. It is a measure of how strongly systems are entangled. Two regions of space are close, not because they occupy nearby coordinates, but because their underlying quantum states are highly correlated. Geometry becomes a large-scale reflection of informational structure. This reverses the usual picture. We do not start with space and place quantum systems inside it. Instead, space emerges from the network of quantum correlations themselves. If that is correct, then space-time is not the foundation of reality. It is a macroscopic description, similar to temperature or pressure, arising from deeper microscopic data. And that shifts the question again. If space is emergent, and if gravity is emergent, then the three-dimensional world we experience may not be the deepest layer of physical law. It may be a reconstruction, a projection of something more fundamental that does not live in 3 dimensions at all. At this point, it is critical to remove a common misunderstanding. When physicists use the word holographic, they do not mean that the universe is fake, simulated, or visually illusory. A hologram in optics is not unreal. It is a way of encoding 3-dimensional information on a 2-dimensional surface using interference patterns. The key feature of a hologram is not deception, it is encoding. A flat surface can contain enough information to reconstruct a 3-dimensional image. The depth you perceive is not stored as literal thickness. It is recovered from the pattern encoded on the boundary. The holographic principle applies the same logic to space-time. If the maximum information inside a region scales with area, and if gravitational dynamics can be mapped to a lower dimensional quantum theory, then the 3-dimensional bulk may be a reconstruction from boundary data. In this picture, the boundary is not a physical wall you can travel to. It is a mathematical surface that encodes the full state of the system. Everything happening in the interior, particles moving, stars forming, black holes merging, has an equivalent description in terms of quantum interactions on that boundary. Nothing is missing. Nothing is reduced. The two descriptions are dual. This is why the principle is so powerful. It does not say that the interior is an illusion in the sense of being false. It says that the interior is not independent. It is a derived description of underlying information. The depth of space may be analogous to the depth in a holographic image, not stored directly, but reconstructed from encoded correlations, and if that reconstruction is exact, then what we call physical reality is one of two mathematically equivalent ways of describing the same information, which forces a more precise question. If two radically different descriptions, one with gravity in 3 dimensions, one without gravity in fewer dimensions, are fully equivalent, which one is more fundamental? Up to this point, the strongest version of the holographic principle comes from a very specific setting, anti-de Sitter space, a universe with a constant negative curvature. Our universe is not anti-de Sitter. Observations show that cosmic expansion is accelerating, which suggests a small positive cosmological constant. The large-scale geometry of our universe more closely resembles de Sitter space. This matters. The ADS/CFT correspondence is mathematically precise in its original framework. For our universe, an equally exact duality has not yet been established. There is no complete, universally accepted holographic model of cosmology. That is the current limitation. However, several lines of research suggest that holographic ideas are not confined to one special geometry. First, the entropy bounds derived from black holes do not depend on anti-de Sitter space. The Bekenstein bound and related entropy limits apply much more generally. They still point toward a maximum information capacity scaling with area. Second, attempts to formulate holographic descriptions of de Sitter space are ongoing. While less complete, they indicate that similar boundary-based encodings may exist for expanding universes. Third, independent research into quantum gravity, including tensor networks and entanglement-based reconstructions of spacetime, continues to show that geometric structure can emerge from purely quantum information. So while we do not yet have a finished holographic theory of our universe, the conceptual pattern keeps repeating. Whenever gravity and quantum mechanics are forced to coexist consistently, information appears to organize itself in ways that privilege boundaries over volumes. This does not prove that our universe is holographic, but it does narrow the options. Either holography is a powerful mathematical coincidence limited to special cases, or it is revealing a structural feature of reality that we are only beginning to understand. And if the second possibility is true, then the next step is unavoidable. If the universe is fundamentally described by information on a boundary, what does that imply about matter, particles, and even ourselves? If the holographic principle is correct in a deep sense, then matter is not fundamental in the way we normally assume. In standard physics, particles are treated as excitations of quantum fields that exist in space-time. Fields are defined at every point in space. Geometry is the background. Matter lives inside it. But in a holographic framework, the hierarchy shifts. The boundary theory contains no gravity and no additional spatial depth. It contains quantum degrees of freedom arranged on a lower dimensional surface. Yet when those degrees of freedom are translated into the bulk description, they produce not only particles, but curved spacetime itself. In other words, what we call a particle moving through space may correspond to a specific pattern of quantum information evolving on a boundary. Mass becomes a feature of how information is organized. Forces become features of how correlations change over time. Gravity becomes a geometric reflection of entanglement structure. This does not remove physical reality. It redefines its basis. The bulk description, the one we experience, is effective. It is valid. It produces correct predictions, but it may not be the deepest layer. This is similar to how temperature works. Temperature is real and measurable. It has predictive power, but it is not fundamental. It emerges from the statistical behavior of microscopic particles. In the same way, space-time and particles may be emergent variables arising from more primitive informational degrees of freedom. If that is true, then the distinction between space and what is in space dissolves. Both are different expressions of the same underlying data, and that includes observers, our brains, our bodies, our sense of motion through space. All of it would correspond to highly structured patterns within a boundary-level quantum system. That conclusion is not mystical. It is a logical extension of the framework. If the entire three-dimensional universe is dual to a lower dimensional information structure, then we are not entities embedded in fundamental space. We are stable informational configurations within a system whose deepest description may not involve space at all. Which leaves one final issue. Even if this structure is mathematically consistent, does it change anything about how reality is experienced? Or is it simply a different language for the same physics? At this point, we need to separate two possibilities. The first is conservative. Holography is simply a powerful mathematical duality. It provides two equivalent descriptions of the same physics. One uses gravity in 3 spatial dimensions. The other uses a lower dimensional quantum theory without gravity. Both produce identical predictions for observable phenomena. If that is the case, then nothing changes physically. We continue to measure particles, curvature, radiation, and expansion exactly as before. The holographic principle would be a deeper language, not a different universe. But the second possibility is more disruptive. If space-time and gravity are emergent, if they arise from underlying quantum information, then our most basic intuitions about locality and distance are not fundamental truths. They are large-scale approximations. In everyday physics, locality means that interactions occur at specific points in space. Causes propagate through space over time. Distance limits influence. In a holographic framework, locality may itself emerge from patterns of entanglement. The apparent separation between two regions of space could reflect weak informational correlation rather than intrinsic geometric distance. This has measurable consequences at extreme scales. In black hole physics, it reframes the information paradox. In quantum gravity research, it reshapes how singularities are treated. In high-energy theory, it provides computational tools that would otherwise be impossible. So, holography is not just philosophical, it has operational value. However, there is an important limit. We do not yet have experimental confirmation that our universe is holographic in the strong sense. The principle is consistent with known physics. It is supported by rigorous mathematics in specific geometries. But it is not a completed empirical theory of cosmology. That distinction matters. The holographic principle currently stands as one of the most serious candidates for unifying gravity and quantum mechanics. It suggests that information is not something stored in space. It is something from which space is constructed. If that is correct, then the deepest layer of reality is not geometric. It is informational. And what we call the universe, with its depth, curvature, and motion, may be a large-scale reconstruction of that information, perceived from within. The final question is not whether the universe is an illusion. The final question is whether geometry is the right starting point at all, or whether information is the true foundation from which everything else emerges. For centuries, physics treated space and time as the foundation of reality. Events happened somewhere. Motion unfolded through distance. Gravity curved geometry. That framework worked, and it still works, at every scale we can directly observe. But black holes forced a correction. Entropy scales with area, not volume. Information refuses to disappear. Gravity and quantum mechanics demand consistency. And when those demands are followed to their logical conclusion, space-time begins to look less like a starting point and more like a consequence. The holographic principle does not claim that the universe is unreal. It does not reduce existence to a trick of perception. What it suggests is more precise. The three-dimensional world we experience may be one description of a deeper informational structure defined on a lower dimensional boundary. Geometry may emerge from entanglement. Gravity may emerge from quantum correlations. Distance may reflect degrees of information, not fundamental separation. This is not confirmed cosmology. It is not finished theory. But it is one of the most coherent attempts to reconcile the two pillars of modern physics, general relativity and quantum mechanics. If it is correct, then space is not the container of reality. It is the interface, and that reframes everything. Because once space is no longer fundamental, the next layer down is no longer geometry, it is information. And if information is primary, then the universe is not built from matter arranged in space. It is built from structure encoded at its limits, which leads directly to the next question. If reality is written in information, what is the language it is written in?